Hello everybody and welcome to Rudy's Electronics Lab. Today I want to talk a bit about a new GPS Disciplined Oscillator that I added to my lab, one by Leo Bodnar, a UK company. And this is going to replace one of my older units that I got right over here that has a little bit problems here. And in this episode, I don't want to talk right away about this unit, but I want to talk a little bit first about time and frequency measurement and accuracy, because this is actually a rather interesting field of metrology, I think. And I also want to show you some super precise clocks that I went to see myself when I had a recent visit to Germany. Then I'm going to talk about the specific unit here that I'm reviewing today, the Leo Bodnar unit. I'm going to talk about a number of different aspects, also some aspects like powering and sine versus square wave generation. And then I want to look more specifically also in the computer apps that come with the Leo Bodnar unit, because there's some interesting things going on and there are remarkable differences between the computer software for the different models there, where we can learn a little bit about, but we can also learn a little bit about the hardware of the devices. And finally, I want to test my new clock a little bit and I want to compare how my older clocks are doing. I took some of my measurement instruments here with presumably the best clocks that I got in the house, but I don't know how good they are. And we can safely assume that this clock is going to be much better. And so we can see how my existing clocks are performing. But first a little bit about understanding time and frequency measurement. And when we want to measure things, for example, like from the SI base quantities, etc. Base quantities like length in meters and weight in kilograms. Well, actually it's mass in kilograms, I should say. Time in seconds, etc. Generally speaking, it requires two things. It requires to be able to measure something accurately, and it requires an appropriate standard against which you are measuring it. Now, generally speaking, if you're able to measure all these type of quantities that we see right here with an uncertainty with 1 part per million, then you're already doing a pretty good job. That already requires good instruments and knowledge how to use them, etc. And let's take a look, for example, at measuring voltage. We are a channel about electrical engineering here. A voltage is not an SI unit in itself, but is a derived unit. Current in ampere is an SI unit, by the way. So measuring voltage. So I think one of the go-to devices, if you really want to measure voltage very accurately, would, for example, be the Keysight 3458A. A famous meter, has been in the market for long, there's already several revisions internally to the device. It's considered to be one of the most accurate devices that money can buy for general purposes. And how accurate is it? According to the spec sheets, the accuracy is 8 ppm, so 8 part per million. And optionally you can get it with a slightly better accuracy of 4 ppm. So that's kind of the accuracy that we can get to. And this is a meter used by a lot of professionals, and you even find them in the calibration lab. Here you see a picture that's actually in a YouTube video by Marco Reps when he's visiting PTB in Germany. Actually, I'll come later back in this video talking about PTB. And so these units, you see them right over here, the Keysight unit. I think they're only like one step away or so from their calibration standard in the lab. And that calibration standard is very precise. I believe it's a Johnson effect or a Johnson junction as it's called. And that is a phenomenon that actually uses superconductors. Two superconductors are placed in close proximity. And that's a very precise source. So the source is going to be super precise, but the measurement is still limited to what these measurement devices can do. So, okay, we got this Keysight meter here. We can measure about 1 ppm or 4 ppm, a little bit worse than that. So that is great. However, if we want to measure time or frequency, it's 1 over time, etc., then even today's stuff in the lab that I'm going to talk about can be about 1 million times as accurate. We're talking about 10 to the minus 12 rather than 10 to the minus 6 that we talked about voltage. And the really best clock in the world basically can get like 1 billion times better than our Keysight meter. So that's quite amazing. We can measure time so much more accurate than we can measure things like voltage, current, and all type of other stuff. So I want to look a little bit at the different type of time standards basically that we got and their stability and understand their the accuracy. So we would start with a regular type of crystal. We have it in plenty devices. We have it in quartz watches, about all the devices, every computer for the clock, etc. So we're talking about 10 minus 5, so 10 ppm basically of accuracy. If we want to get that a little bit better, the first step we will be taking is doing some temperature compensation, because temperature is one of the main parameters to which the crystal frequency depends on. So basically we can compensate the temperature with some smart circuitry. We can even do that a bit smarter with going microprocessor control things. We can get to 10 minus 8. And what is a quite common thing to do if you need a very precise clock, that you take a crystal and put it in an oven and put it at a constant temperature. I think it's like 60 or 80 degrees Celsius, and at that constant temperature the crystal is going to be behaving in a more accurate way, in a more predictable type of way. That is actually the type of crystal that is right now in these two devices. Both of them are equipped with overniced oscillators. We are at 10 minus 8. If we still want to go one step better, we can go to a rubidium atomic frequency standard. Now these are already quite a bit more expensive, but they might be still affordable for a general lab and perhaps even for a hobby type of lab. And if you really have to go one step further there, you might go already to a better lab standard, but I don't think a lot of people would have that privately at home. That would be a Caesium atomic frequency standard. But you got commercial devices. I think I looked up something. I think you're talking 30, 50,000 units in that range or so. And then the very, very good clocks, and when I talk about very, very good clocks, I talk about the type of clocks that you would find at the National Metrology type of institute. There you would have atom clocks like the Caesium fountain clock with the accuracy of 10 to minus 14. There are even better clocks basically that are laser cooled fountain clocks. We talk about minus 15. This is fascinating, by the way. They're using a laser to cool down a clock. So the laser doesn't warm it up, but it cools it down instead. And I've been explained they do that by basically giving laser beams to an atom exactly at the point where they start moving in a certain direction. This way they are suppressing the movement until they don't move at all, and well, no motion basically is 0 Kelvin. Huh? So laser cooled basically. And the very best clock they got out there is basically the optical clocks right now that are working on quantum mechanisms like trapped ions. These are experimental still, and there we have an accuracy of 10 minus 18, what I already mentioned. Now, what is the exciting thing about this type of clocks in the lab that I'm going to talk about today, the GPS Disciplined Oscillator? Basically, you're combining the best of both worlds. You're combining basically the relatively good accuracy on the short term that we got with a good crystal, that might be temperature controlled or overnight or so, together with the long-term type of stability that is offered by the GPS system, which on the long term is very good, but if you take it like receiving as you got it here on the ground level, it might suffer from drift and a couple of other times. Combining these two things by using the GPS signal to discipline the local oscillator, basically, we're getting the best of both worlds, and actually for a fairly modest sum of money, for a couple of €100, even less, you can buy devices do exactly that. And then we're at 10 minus 12 or so. I should emphasize that this overview is simplified and more or less indicative. The exact accuracy depends a little bit on the devices. There's going to be some ranges. I didn't work it out in great detail. Also here I'm not differentiating between short-term stability really and longer-term stability, like aging over years or so. So you can go obviously into a much higher level of detail. Now, how do these very good clocks look like that we got like in national standards that's so being used? Now, a while ago I was doing some work with a colleague at PTB in Germany, in Braunschweig, and that is the National Metrology Institute of Germany. And there are also all these very precise clocks that I got around. So together with the colleagues that I was there working with, they were happy also to have a walk around the laboratory, the premises, and go to I think what they call the Uhrhalle, where the clocks are, famous clocks in Germany. And we went to look at a couple of them. And actually you see a picture here, and we're looking at their CS2 clock. So that clock's been used for a very long time to create the official time in Germany. And this clock has an uncertainty of 12 to the minus 15, so about 1 to the minus 14 or so. So that's already a pretty precise clock. But they got even better clocks in Braunschweig. Here you got a bit of an overview of the various clocks that they have. I'm going to leave some of the sources in the last sheet at the end of this set. So the clock that we were just looking at, the CS2 clock, that is a 12 to 10 to the minus 15 clock. A better clock that I got, which is like a fountain clock, a cold atom. So again, basically using lasers to cool it down. It's at 10 minus 15. And actually these, they got two clocks of each of these types. These 4 clocks are actually the official German legal time. So some people basically say there is no uncertainty. This is defined as the legal time. But that's of course how you want to take it. But then they also got some of these really even better clocks there. And one of the clocks they're having down there in the laboratory is an optical clock based on quantum mechanics basically. And it's a trapped ion clock. And this is more in the research phase. These are not the official legal time clocks or anything. 3 times 10 to minus 18, an incredible type of accuracy. So what does that really mean? It means that a clock like that has an uncertainty of about 1 second over the full age of the universe. Can you believe it? That's how precise these clocks can go. Well, obviously at home we don't need clocks of that type of precision, but you know, the cool thing is that we can tap into these very precise clocks. So the CS1 and 2 clocks and CFS clocks, you can basically tap in it by the radio time signal that all our little alarm clocks are using. It's connected to that, and basically also GPS satellites. In a similar way, we are piggying back on some very good clocks that are also disciplined on the longer term. So that's kind of an exciting thing to do. And this whole idea that we're moving towards using physical parameters, physical behavior, but also quantum type of behavior, really moved the field of metrology forward. And of course, when I was visiting colleagues in Braunschweig, I was also interested to see this very best clock they got over there. So we actually took a little visit there, and right here you got it. This is a trapped ion setup here. Right now it is not functioning as a clock. Right now this installation is being used for characterizing qubits of a supercomputer, but we're basically talking about the same setup here. And so we also see the laser cooling part, the qubit in question where the trapped ion is, that's in the round cylinder that you see in the right top, and you see the laser construction to cool it down. You see a couple of cameras to read out and try to see how these trapped ions are behaving themselves, and a bunch of servo and control electronics and optics basically around it. A super cool setup, and we're very thankful to our German colleagues to go and see it. Now we see this phenomenon of using like physical constraints or physical behavior or basically quantum behavior, etc. Yeah, that is kind of what is bringing the metrology field forward a lot right now. You can do things much more precise than having a length unit of a meter. Actually, as we all know, had a length unit originally of a meter in Paris, and the weight of the mass, I should say, of a kilo in Paris. Already long ago, I think 100 years ago, people already found out there was a big issue. They made like the international reference for the mass, the kilo. Then they had like national reference that could be used on national level. And once in a while, they were bringing back their national references back to the international one just to check if everything was still okay. And they found out that the international one was kind of missing significant mass. And it's still a mystery where it lost the mass, but if you compare it to all the copies were kind of still good and the original wasn't. That was already telling us that this type of sources like the weight of a kilo, the mass of a kilo, wasn't doing it. So we need to define them in other ways and measure them in different ways. And that is also what now the SI system is doing. There was a recent revision in 2019 redefining several of the properties in the SI system, and basically now almost all of them are based on a quantum type of behavior, or basically, yeah, either directly or deriving from it. So the second is a source basically for other types of measurement, like length, that we define as the time it takes for light to travel. Now, let's move now to the actual devices that I want to look at today. GPS disciplined oscillators, a fascinating type of devices, very affordable but at incredible performance. And there's a lot of offerings on the market. If you go to eBay or sites like that, you find plenty of units. I'm showing a number here. And the one on the left bottom, actually, that's the unit I've been using here for the last couple of years or so. But it starts to have trouble. It doesn't seem to lock itself well anymore. Well, the lock light is very dimly brighting, and there's one of the alarm lights on, and I also had to replace the power supply already a couple of times. And on top, it's using more energy than I like it to use. And this is the only device in my lab that is powered like all day long, every day of the year. And I want to kind of to bring that down. So I thought I should go to a brand new unit anyway. Let me say still a couple of more things about this unit because it's kind of exciting. Oh yeah, maybe first of all, I actually built some additions to it. I built a nice frequency divider. Because we only got one 10 megahertz clock here, and this way we have a couple of different frequencies coming out, 1 megahertz, 100 kilohertz, and a couple of other things, 5 megahertz, and also some selectable type of frequency. It's a very nice design by David Partridge from the UK, I assume, who has shared this design. You can take a look at it. Yeah, he did some nice design consideration also to make the output correctly in sync and to make it fast enough, the pulses and the drive capability. So there are a lot of nice things from this design. And it's also a nice project basically to exercise a bit on SMD soldering, which is one of the reasons that I did that. I also built a clock distributor for my lab. It got six outputs, and this way I can connect a variety of my devices to the same reference clocks, and all the outputs are electrically isolated by transformers to prevent any ground loops. Yeah, so these are fun things that I built on top of my unit here. But what's going on inside that unit is also kind of interesting, because like many units that are sold on eBay, etc., the actual disciplined oscillator in here is not a new one, but it is a second-hand one. It comes from another device that was taken off the market or decommissioned or so, and eventually they bought this unit and put them in this box here and put a display with it and gave it a new life. So where do these units really come from? Well, you can actually kind of I found it out myself by connecting something to the serial port here, and you can use a bit of a language to do queries and control the whole device and read out all the values. And one of the interesting things is that you can read out the flash memory out of the device, including all the past GPS locations where this device has been taken into or has served basically. So I've been looking a little bit into that and reading out these values in the flash memory. I came to 2 locations where the device has served really. And the first location when it was first turned on for I think some 6 months or so was a location in South Korea. If I add in these GPS coordinates in Google Maps, I'm actually getting at the Samsung Electronics Smart City campus, and I see the precise roof of the factory where the antenna of the device was. So it was produced and tested over there basically before it was shipped to a customer. And then the next location where the device served, I think for some 6 or 8 years or so, happened to be in Japan, and it was in Yokohama. And when I typed that address basically into Google Maps, I see a street, and if I go to Street View, I could have gone there. I was in Japan a couple of times pretty close by, but I didn't go to this particular location. But if I use Google Street View, I actually see a cell tower. So this was actually a device that was was part of a base station for a mobile, for a cellular network. And these type of base stations actually needed precise frequency sources to work well. So yeah, these units served there for a number of years, up to the point where they were replaced with a new generation of base station electronics, and then they were like traded secondhand and ended up in units like this one. Now let's go and talk a little bit about the different type of devices that Leo Bodnar offer, what I eventually bought. And so he has two new models that came out just like in last year somewhere. And he also has some older models, of which the most original one came out in 2015, and a little bit later a small one single channel version came out of that as well. On this sheet you see the specs of the devices being sold by Leo Bodnar right now, and the two top ones are the devices that were introduced last year, and then we got the two precision model, the mini precision and the normal precision, that are the older devices. And we have devices with one output and two output for both generations. The interesting thing is that with the Leo Bodnar devices, in contrast to most GPS disciplined oscillators, that you can choose your own output frequency, and in some of the models all the way between 1 Hz and 1.5 gigahertz or so. That makes them very, very powerful. It has some implications, by the way, which I will get to in a second. The new models, basically you can set any frequency for any of the two outputs. The other devices were more limited there because the second output had to be a fractional multiple of the master frequency of the first channel, but that's not anymore the case. Then in the new 2-port channel we got a 1 pulse per second mode, as we also find on other GPS disciplined oscillators on the market. And you might wonder, isn't that the same as just the 1 Hz mode? But it's not, because 1 Hz is actually a 50% duty cycle. The 1 pulse per second is a much shorter pulse. I haven't measured exactly, I don't remember how much shorter it is. And you also see a little light brightly flashing on the unit if that mode is selected. Output levels are 3.3 volts into 50 ohms. The new models have like a choice between high and low power mode, and the high power mode is equivalent to 10.3 dBm. I measured that myself. All the other specs on these sheets are the specifications on the website, basically. The older devices, you could set the power mode in, I think, 5 different levels defined in milliamps. Output connector styles SMA. For the modern ones, the very oldest one has BNC connectors. Phase noise, these are the specs, looks very nice to me. I'm not really into that, cannot measure it myself anyway, so I'm gonna skip that. Rise fall times, on the new model they're published in the 300 picosecond. That is pretty fast, and that also allows the device being used for other purposes, like characterizing, for example, the analog bandwidth of oscilloscopes. Because this is way faster than oscilloscopes up to say 500 megahertz or 1 gigahertz channels or so. And then finally the powering. The very oldest device could be powered by either USB-B bus power or via DC input. And the new models are USB bus powered. And there comes a little bit of an issue for me. Because if you use USB bus power, the computer basically I connect only very incidentally to the unit. That's to set a frequency maybe, or to check some GPS parameter. But then I'll probably turn off my computer or take my laptop away or whatever. I want the unit to continue and not to lose its sync basically and its discipline. And I don't like that. So what I did in the end, that I tried to build it a bit myself, I made a little sandwich here, and the sandwich is a USB 2 hub, an old one, with basically the unit here, and something else I'll tell you in a second. But this way basically I can keep the unit powered all the time and just connect a laptop incidentally without taking away its power, and that works perfectly fine. I connected a DC power supply to the USB hub here. Funny enough, I had a whole bunch of old mobile phones power supplies that were rated at 5 volts. But actually when I measured them under a small load, they were actually producing like 8 or 9 volts. So let there be a warning. Always measure your power supply before you connect. I did that happily enough. Otherwise I might have broken my new device here. So that's kind of the solution here. You might consider a similar type of thing. And you will also see in the sandwich there's another unit over here, and we need to talk about that, because the thing is that the Leo Bodnar units basically produce square waves, and that's different from most of the other GPS disciplined oscillators on the market that generate sine waves. And I've read some critique on that, and I can stand it, but I don't totally agree with that critique. So it's a bit a matter of preferences, square wave versus sine wave. With square waves, you might be interested, for example, in more time dimensions, etc. You might be interested in the rise time and fall time, like I said. It can characterize scope, and you get like all these high harmonics. And you might have instruments in which you might be interested to have that. On the other hand, the sine wave is nice and clean. It would reduce any risk if you're concerned about that, about radiation of all these harmonics, if you might be doing very sensitive things in the lab. If you're really worried about that, by the way, I would recommend that you would just terminate the outputs with 50 ohm terminators. You probably know them already from BNC, but you also have that for SMA. I have a couple of them up in the lab, so you can put that there. In order still to have a sine wave type of thing, Leo Bodnar sells this low pass filter, and then you get like a very nice sine wave. And as you can see here on the sheet, with that filter, basically the harmonics are very nicely suppressed. And the insertion loss is very limited. It's less than 1 dB or so. I also measured that myself, and it's perfectly fine for my type of purposes. I also characterize the filter using a vector network analyzer, and you basically see that it very nicely suppresses rather effectively like the high harmonics. They're not exactly on those points. You can't expect that anyway with this type of analog type of filter, but it does really a good job at pushing them down at the points where you need to have them pushed down. Now, about the criticism of these people, I think the thing is that the Leo Bodnar unit basically can deliver any frequency, and one thing that at the same time as a sine wave, that is kind of an unrealistic thing to have, because then you would actually have to build all this type of circuitry into it that you find in a very fancy and expensive signal generator to create any type of output without all these harmonics, etc. I think that's completely out of the context of a little device like this. So if you want its frequency to be selectable and not fixed at 10 megahertz, then I think you basically will have to live with the sine wave thing. And adding then a low pass filter only for 10 megahertz in case you want to use it for this type of timing things, etc. I think then you're basically perfectly fine. So I like this kind of combination, and I think it comes from the fact that this is a flexible device rather than being a limitation, I think, in a way. But well, it's up to you what you think about it. My old GPS disciplines oscillator was connected 24/7 to power, so it stays locked all the time. Well, not anymore, it's broken now. But it's using quite a bit of power. This is the total power consumption of the adapter to the power grid, about 5 watts or so. So I was kind of interested to learn whether the new unit would perform any better there. So let's get the old one out of the way. Let me connect the new unit. And let's see how much power it is drawing. Okay, so to the power supply, it's about half of it, 2.6 watts. And that is the whole combination of the Leo Bodnar unit. It is the USB switch that I piggybacked on it. And it is the power supply, which is going to be imperfect as well. We can also take a closer look into what the Bodnar itself is really using. So I connected up here the DMM here, where I can measure both power and voltage. I made a Y cable to the USB connection here, so the voltage is going to be reverted. So let's go and see. Voltage of 4.8 volts, so it's plus actually. So that is just fine. Let us see how much power it is drawing. It seems more 300 milliwatts. they published a maximum of 250, but it seems to be a little bit bigger than that. Let me also go and look at the graph here. Yeah, and we see a bit of peaks here. The minimum seems to be at about, yeah, slightly over 300, and it gets some peaks to a little bit more, 327. That's not an enormous difference. But we see that the power use comes with little peaks, and sometimes you got a moment where I think it's kind of reading out a signal or doing something else inside or so. So power use is slightly more than I expected it to be for the unit. At least slightly more than what is advertised. I also see that the unit is getting mildly warm with continuous use. I will use a temperature meter, so we're gonna see a bit how warm it's getting. But anyway, I might not be powering this unit all the time, maybe only when the lab is on, because it seems to lock quite fast. I have to look a little bit more into this. But if PLL lock is actually as fast as it seems to be, there's no need anymore to have it 24/7 on. And yeah, then power consumption is not much of a concern on my side anymore. And it increases the lifetime of the device as well, I would expect. We're now going to look into the software of the GPS Disciplines Oscillator, and there are a couple of reasons for that. One of them is that it learns us a little bit more about the hardware, but also there are remarkable differences between the software, and we get some functionalities for the one version and not for the other version, and it also tells a little bit where we might want this to go in the future. So I'm showing here kind of the software for the new devices on the top, both as a Windows version and a macOS version, and for the older models, the Precision and the Mini Precision at the bottom. Again, left side Windows OS, right side Mac OS. And you can already see how wildly different all these versions are. And I'm going to explore that into more detail now. So let's focus first on the new devices, where I got like so I've been trying to make an overview of all these software support things and difference and put them all together in a table. And you can see, yeah, quite a lot of difference here. Some of them might be induced by hardware, but a lot of them certainly not. I also had a little chat with people at Leo Bodnar. They were very friendly, so thank you for that. And they also corrected a couple of things in this table, this version that you see here is the corrected, updated version. First, we're going to look at the new devices. We're going to look at the Windows version on the left and at the Mac version on the right. It all looks very different already, as you notice. And if we put some colors there, we got green for what is similar. We got red for which is only in one version but not in the other one. And we got blue for something that's in both versions but implemented in a different way. Let's look at it, one by one. So first, what is shared basically is some basic information about the device. I don't want to go in great detail, except that you see that the serial number is presented in a different way. I'll get to that in a second. Secondly, the setting of the output frequencies. As I said, they can be set completely independent of each other. And here we still got the same features across the two different operating systems. We got the 1 pulse per second mode, we got the low power frequencies that we can enable or disable the outputs, but only both of them at the same time. And we got a FLL mode. I believe it's frequency lock mode opposed to phase lock mode. So here we're still the same. But now we're getting into the differences. What do we get on the Windows version that we're not getting on the Mac version? Well, it's showing the UTC time of the GPS satellite. Okay, that's nice. Second, we got a button for NMEA. This is basically the often used protocol for maritime communication for GPS and other types of devices. And I didn't fully understand what this button was doing, because this information comes out of the device via the USB interface, and actually be using it. I'm going to show that in a moment, but I don't really see didn't see why there was another switch for that. And then when I talked to the people at Leo Bodnar, they explained me that actually with this switch you can create a second copy of that information, and then it comes out as a serial data stream over output 1. In addition to the one already on the USB port, which is a visual COM port that you can use there. And that might be interesting if you're using some legacy type of devices that want this as a serial RS-232 bit stream. Mind you, by the way, that is a 3.3 volt signal, and depending on the other device you might need to do some signal level adaptation. But yeah, provide some flexibility. It's nice it's it's there. Another thing is that we see is the levels of each of the satellites received, but we also see the average level of the satellites that are received or used. That is not completely clear, by the way, to me. On the Windows version, we also get to see the different types of global navigation satellite system, the different types of GNSSs. And you see here GPS, all the other ones, etc. And the nice thing that you can click them in any combination and you see then those satellites levels that are selected for that thing. The only thing is that Baidu and GLONASS cannot be selected at the same time. They're mutually exclusive. There's probably some good reason for that. But it's nice that we can select them and see them here. We also got dynamic models for airborne, for stationary, I believe. There's one more, you can see it in my table somewhere. Finally, we got diagnostics. It opens up a web page, shows you stuff. Well, not a web page, but it shows up a browser showing you stuff. And there's a factory reset. So all these things are only on the Windows version and not on the Mac version. However, on the Mac version, we got other stuff. On the Mac version, we can actually connect multiple devices at the same time. And we see them by their serial number. And we got a blink LED option, which make the LEDs blink on the device that you selected. Makes sense in combination with being able to select devices, right? So in a bigger setting where you want to create like 5 different frequencies with 3 devices or so, yeah, so this is a nice feature. We also get like to see the different satellites and their strength, but here we don't get to see the average strength of the satellite, but we do get to see the satellites that are used and not used for determining the signal. So the green indicated ones are used and the red ones are being ignored even if they are received. And we do get to see a map, which we don't get to see on the Windows version. And there's one other thing, and this is kind of important. There is a status line that tells us something about the locking status, and on the Windows application on the left, I think you can either get one of 2 messages. It's either no GPS signal or GPS signal OK. On the macOS version, there are only 2 messages here that you can get, I think, and it is no GPS lock and it's device OK. I don't really get why this slightly different language, and there's a bigger underlying issue that is, it is not really super clear to me what is exactly locked here. Because if I look at other GPS disciplines oscillator, you basically have the satellite lock part of it, that's the GPS lock if you want to call it that way, and there's the PLL lock. And I think then you can also associate PLL lock with the device being disciplined. That might be a third thing actually or so. Often take like much longer before the last situation is achieved. Some of my older devices that took like 12 hours or 24 hours, I think, even to do that. Now here we're only getting this information, and I asked basically the people at Leo Bodnar about it, and they said, well, with this new hardware it's basically the same thing. So once you get like the OK thing, then basically it's both GPS lock and PLL lock. Yeah, so I take that message for what it is. I'm not exactly sure at what point we're actually into the fullest accuracy of the device or not, but maybe, yeah. And then we come to the other point, there is no manual, and this is really something I would like to learn from a manual. Detailed information about how it really works, how the locking situation is, etc. That is really one thing that, if anything, could be improved here. I think it will be a good manual with the device. Now, I also want to look a little bit at the software for the older device. It learns us something about the hardware difference between the devices, but also a couple of functionalities that might be brought to the newer types of software here. So I'm showing the Windows app here to the left for the 2-channel device. At the top right, I'm showing the Windows version for the 1-channel device, and at the right bottom, the software for the macOS device. And again, all 3 of them totally different. Quite interesting. I have to tell you, by the way, that with these screen prints, particularly the one of the Mac, I've been editing them a little bit from different screenshots to put things together. The reason is that some of the screenshots are actually by myself and some of them are from the website. I couldn't get it at the same time, and I don't have these devices, so I cannot start them fully up with the content in there. So I put things together as I think it should look like in the actual view if you would have the hardware connected, but just for your full disclosure. Okay, let's go take a look at it. Let's go right away to what I consider one of the most important things, that is the lock thing. And therefore I go to another version of the Windows software actually, where we see at the bottom, we get to see no GPS signal, no PLL log. And on the Mac version, we also got little lights on our screen that are showing that. There we get in the type of status information that are kind of, yeah, not so clear information, I think, with the current software. So that's something I would really like to see improve there. Looking at some of the other differences between the devices, concerning the output settings, we can enable and disable individual outputs. We cannot do that on the new devices. We got an identify button where we can see a little light for which is which basically on the device. That is a nice thing as well. And we also get a phase shift between the two channels. That's kind of interesting. I don't know the new devices when things are in phase shift, at least if that's possible because of the choices that you make. There's a hardware hardware dimension to that as well. But yeah, that was in the old version. I will be interested in the new version, how that works and whether that will be possible, perhaps for particular type of settings when there are multiples of each other. In the old software, at least in the Mac version again, you had a sleep functionality. I thought it was kind of a nice idea because what I would like in terms of sleeping of the device, which is not on the new devices software right now, is that you can bring like the output stuff to a stop and all the lights, and that you would only keep the GPS unit up for PLL type of purposes. But actually when I asked the people of Leo Bodnar about this, they explained me that in this old version the sleep was actually another type of function meant for people that using it as a reference clock for audio application. It was turning the satellite part off. Yeah, so that's another thing, but it's not exactly the type of sleep thing that actually I might be interested on the device. But maybe in the future we'll have some kind of sleep option on the device. And then finally, yeah, I already mentioned this NMEA date. I hope I'm saying is right. Is standard for maritime type of things. Yeah, that is implemented over the serial port, and actually that means that you can use any type of generic type of software that works with that data. And here on the Mac computer, I'm using a program called GPS Dashboard. It is by Kevinnovate, and it's great. You can see the satellite position. If you wait much longer, you're going to see the trails of the satellite. We can get a map. We can see the signal strength of all the satellites and their identity, but also how they develop over time. Super useful if you're moving or want to find the right spot to put your antenna, for example. Yeah, we got all types of other types of information. We can even start an NTP time server on the computer. Yeah, great, and it's good to see that it properly works with this Leo Bodnar unit. I would now like to compare the new Leo Bodnar to the existing clock sources I have at home. So I must assume that the Leo Bodnar is way more accurate than the others one, so it can serve as a reference point here. So I prepared the oscilloscope here, and we got the Leo Bodnar coming in here on channel number 1, and then I've connected each of these devices to another channel. I actually took two CMU 200s of Rodi and Swartz, and I took a Anritsu vector signal generator. So let's go and see, and we'll start with the CMU 200 right on the top of it. Let's activate that channel. And look at that. We basically see that, yeah, it's 10 megahertz as well. We can measure it down here, but it doesn't make a lot of sense because its own internal source here is another source of variation. So it's better just to compare the two incoming sources here. So we basically see it moving compared to that. So we know it's not exactly 10 megahertz, but it's not terribly far off either. It's moving like 1 second every waveform. And if we will be at 1 megahertz, then moving every second will be 1 out of a million, so 1 ppm. But we're at 10 megahertz and then moving for 1 second, it's only tenths of that, so 0.1 ppm. Let's see how the next one is doing, because this one has the B11 clock option. So that is better than the standard, but this one actually has the best one, the overnized option. So let's see if this one indeed is better. I mean, these are all devices and they have drifted over time. You can adjust them, but hopefully this one has stayed a little bit better because it has the the most expensive clock option. So let's go and take a look at it. And look at that, it looks rock steady, at least if you look at it this way. You actually see these are square wave devices versus the sine that I'm getting out of my Bodnar right now. So it doesn't move a whole lot at all, so it seemed to have not drifted much at all over its history. And now let's take a look at the Anritsu. And there we go. It's also moving. It's moving a little bit less than the top unit there, but it's also slightly off. All these devices have been running for a couple of hours already here today, so they're already at the operating type of temperature. How can we now exactly say how much they're off? I think that's a little bit easy to do in the XY mode. So let me just prepare a setup. Let's load the setup. It's always nice. You can see the full example already here. I think here I got my XI example. There we go. And now I basically put the top one and the bottom one here. And we can observe here basically how often of how many seconds it takes basically. So this one is basically going opening and closing fully like every second or so. So it's 0.1 ppm off. This is a little bit slower here because, or a little bit more accurate because it takes 2 or 3 seconds to go through the whole cycle here. And let us then see how the most accurate one is behaving. So we need to select its signal here. This is also nice, this scope we can have 2 XY diagrams at the same time. So let me get channel 3 here. So it looks like rock steady, but if we have a little bit more of patience, you will actually see that very slowly this will be closing as well, like the other one. We just need a little bit more patience, but it's getting smaller here, but it might take, I don't know, a minute, a couple of minutes or so. So again, we could use this methodology to calculate how far off the clock is, but it's surely much better than 1 ppm, so 10 to the minus 6. So we talk about 10 minus 7, maybe 10 minus 8 with more than 10 seconds for sure. 10 minus 9, yeah, that would be nice. Huh? Can you see it? It's getting smaller, but it really takes a long time. And having the XY view here is really useful because it's kind of hard to see from the waveform pattern that these two are moving relative to each other. But looking at it in the XY view, you can really well observe that happening. Yeah, you can see it happening. It seems to take minutes, but it is closing down, right? So it is not spot on the same frequency as my Bodnar, but really it's not far off. It's quite satisfying that this device still is as good as it is. Oh, wait a moment, look at this. I was already cleaning everything up and moving my antenna in, and when the antenna of the Bodnar lost GPS, you see it already is way off. That's kind of interesting. You see how it is important that it continuously has its GPS connection. It's continually kind of locking itself to it, and once that it lost, that then it really gets off its own frequency as well very fast. So so continuous reception of the GPS satellite is it's really important for the Bodnar. Okay, quick observation. Now that brings me to the end of this episode. I really like these units. I think they will serve me well in the lab. As you have seen, I've seen a couple of areas for improvement. Is already announced that there's going to be a new version of the Mac OS app, so we're going to see a little bit more support of things over there, etc. In the end, if anything be to be desired, I would say, I already mentioned, a good manual. I'm really missing that. Really go into the details about the locking, about the PLL side, etc. That would be really helpful. Now we kind of have to second guess and get bits and pieces together from the what we can understand from the computer software that comes with, for example. But the manual would kind of be the biggest thing. And otherwise, I think these are very nice units. I think they're sensibly priced. They're very nicely built, etc. well taken care of. So I can, I can totally recommend these devices from Leo Bodnar. Like their pulsar, by the way, I didn't talk about this in this video, but you might have seen it in some of my other videos. A very nice device in which they have an updated version, I think, with a casing around it. Was not yet the case when I bought it a couple of years ago. But great stuff. I'm enjoying it, and it's the end of the episode. Thanks for watching, and hope you come again next time. And oh yeah, subscribe. I should say that. Everybody says that on YouTube. Subscribe to the channel and look at the other episodes. Okay, thanks, and next time.